We have AC circuits, and we're going to be talking about this term called the phasor in just a bit. If you've got your notes out, you could write these down. And by the way, I want to tell you something about this phasor thing. When I learned it for the first time, I learned it in college. And in the class I learned it, they assumed that we already knew this. And I asked them, like, what is it? They're like, oh, just learn it on your own. And for like 2 years, I had no idea how to do phasors. And then I finally just sat down and learned them. And I was like, oh my God, if I knew these 2 years ago, life would have been so much easier. So phasors. Now, AC circuits, you delve more into them if you're going to become an engineering major, especially an electrical engineering major. You're going to be dealing with AC circuits all the time. Physics, we're just going to talk about the theory of it, and we'll probably do like a series circuit with them, and that's it. We don't go any further with the AC circuits that way. If you want to, I could provide you with some reading if you want to go even hardcore on the AC circuits. So before I do the AC circuit, let's draw a simple resistor diagram with a constant voltage. So here you have a battery. We'll call it the voltage of the battery. And we have a resistor. Okay? Nothing too bad here. It's just the voltage of the battery and then the resistor. Now, if we were to plot a voltage versus time graph for this system or this setup right here, it would just be a straight line. That's not a straight line. Oh, that is not a straight line. Oh, that's not a straight line either. That's good enough. That's a straight line. So this is the voltage as a function of time line. So when you turn the switch on, voltage is going to run through here and it's going to stay constant. Nothing too complicated here. And then if we looked at the current as a function of time, well, the current as a function of time would be a value less than that, but it would also be a straight line. Okay? That's current as a function of time. I don't know what I wrote there. Now, the reason why the current is less than the voltage is because of Ohm's law. Current is equal to the voltage divided by the resistance. So it's going to have a value less than R, but it's going to be a straight line. And so this setup right here is called a DC circuit here. DC means direct current. So current is only going in one direction. Okay? Nothing too bad here. Nothing at all. Hopefully this all makes sense. This is great. And everybody is happy. Okay? Good stuff. Now we're going to go into the realm of variable current or alternating current. And so instead of putting our battery symbol, the symbol for alternating current is a squiggly line. Let me draw it over here so you can see it better. So what is that? What is that? Oh, yeah. So that is the symbol for alternating current. It's a voltage, but it's alternating. Okay? So we've talked about alternating current before when we were talking about, let's say, a wire that's looped around and it's a magnetic field present. And this whole setup is rotating. Oops. It's rotating around. So this thing is rotating and the flux is going to be changing back and forth, back and forth. And so you're going to get a high voltage, low voltage, high voltage, low voltage, and it's going to be alternating. This is an electric generator. An electric generator is what gives you that alternating current, that AC current. Okay? So we've got a power supply that's alternating. And we're going to connect a resistor to it. Now, what is the voltage of this? Well, the voltage of an alternating current is going to change with time, and it's going to be given by the equation V max and it's sometimes written as VP, which stands for the peak voltage sine of omega t. Now, if we're talking about the voltage of the power supply, we would put a little d right here, and that's called the driving frequency. So it's what's driving this thing to go back and forth. Okay? And so what would this function look like if we graphed it? Well, it's a sinusoidal graph, so it's going to start at 0, go like that, and come back. So this is the voltage as a function of time. All that makes sense so far, I hope. Now, how frequent is it happening? What's the frequency here? So in the US, every country is going to have a little bit of a different, well, US and then everybody else. We have, I don't know why the US does things differently, but we do. In the US, the frequency of an alternating current. So if you were to look at your outlet, this is your wall outlet. Oh, that's a pretty good wall outlet. If you looked at your wall outlet, there's a frequency at which the current is alternating between the highest voltage to the lowest voltage. That frequency, F, is given by 60 hertz. Okay, so we have a frequency of 60 hertz in the US. So what does 60 hertz means? It means that you are going between this and this 60 times per second. So it's going to alternate between voltages 60 times in 1 second. Now, we have this equation. What about the current? What about the current that's going through this resistor? Well, we have Ohm's law. We can still use it because it's still a resistor and a power supply. So if we use Ohm's law, we're going to have to do a little bit of tricky stuff, just a little bit of things added to it. Where instead of writing it I, we're going to write it as I as a function of t, because now we're dividing it by the voltage divided by the resistance R. And so I, as a function of time, is going to be equal to, where am I going to write this? I'll write it right here. V max sine of omega t divided by R. Now, if you know something about V max divided by R, V max, the voltage divided by the resistance, or the maximum voltage divided by the resistance, is going to give you I max sine of omega d times t. Okay? Now, what's interesting about the voltage and the current, the voltage as a function of time and the current as a function of time, is they are in phase, meaning that they're alternating by the same amount around the same time. So if we were to plot the current as a function of time, it would look exactly like this, except just a little bit less, because the current is the voltage max divided by R. So we're going to have the same frequency. Whoa, there we go. And that is I as a function of t. Or use lowercase I. I is a function of t. So if the voltage goes up, the current goes up at the same time. If the voltage goes down, the current will follow. So whatever the voltage is doing here, the current through the resistor is going to do the same thing. And so we call this being in phase. Now I'm going to show you a new way of representing this. Some of you might have seen this already. Some of you have never seen this before. So if you're watching your Netflix while you're watching me right now at the same time, pause the Netflix for a second and focus your attention to here. So you get it the first time, and tomorrow we'll add to it, and it'll make more and more sense on how we derive some of these equations that come from here. Okay. You turned it off? All right, good. Make sure you've got a cup of water. Take a little sip. Good. And now I'm going to show you the so-called phasor diagram. A phasor diagram is another representation of this diagram right here, of this graph. So in a phasor diagram, we have the y-axis, which is going to be the important axis. That's the only axis we really care about. The x-axis doesn't really matter. And what we're going to do is we're going to represent the voltage and the current as vectors. Okay? So let's look at the voltage first. Sure. I'm going to represent the voltage as an arrow that's this big. And that length from here to here is the voltage maximum. Okay? I'm just putting some values here. And this arrow, this voltage arrow maximum is going to rotate around this coordinate system here. So it's going to be spinning. It's going to start at 0 and it's going to spin. And how much this is going to move is called omega times t. The angular frequency, in this case, would be omega d times t. But that's how fast it's spinning. Okay? So at some time t1, it's going to be right here. At some time t2, it's going to be right here. At some time t3, it's going to be over here. At t4, it's going to be down here. And then it's just going to keep spinning around. And so if we were at 0 degrees, right? If we were at 0 degrees, then we would get something, and then so on. Here's what you need to know about phasors. You don't really care about the size of the arrow right here. What you care about is the arrow's projection. The projection of the arrow tells you the value of the arrow. Now, what do I mean by projection? So this y value here represents numbers like 1, 2, 3, 4, 5, 6. There's no like units here. It's just 1, 2, 3, 4, 5, 6, 7, 8, whatever. If I were right here, if the voltage was located right here, this isn't the actual voltage. The actual voltage would be this big. So we have to make a projection, like a shadow, I guess, over here. And the size of the voltage is actually this big. So when you're at some time t right here, this is the voltage max. As you increase to 90 degrees, the voltage value is going to get bigger and bigger and bigger and bigger and bigger. Right? And so right now, this is the voltage as a function of time at this specific angle. And so we can do a lot of different interesting things here because it represents what's going on here. Let's look at the angle at 0 degrees. So at 0 degrees, you shouldn't get any voltage. Well, let's draw out what that looks like at 0 degrees. At 0 degrees, the voltage maximum would be right here. This is 0 degrees. So the projection of the voltage, if we look at the projection, which we go to the y-axis, is 0. So you don't have any voltage there. And at 0 degrees, you don't have any voltage. And then if we were to go here, which would be pi over 2, that's 90 degrees, then the voltage would be located right here. This is the voltage maximum, V max. And the projection is V max. It's not a part of it. It's the entire thing. So at 90 degrees, when you make a 90 degree, you will be at the maximum voltage. That's what the projection is telling me. Okay. Write yes on the comment section if you understood that. Just a little yes. Okay, good, good. Beautiful. Beautiful, beautiful, beautiful. The reason why we're going to use phasor diagrams is because we don't have to just put voltage here. We could actually put the current here as well. So let's try that again with current. Now, we could write our y-axis just like we did before. Let's look at the current at some value here. So we'll use the current in red. And this is going to be I max. Now, we had said because current and voltage are in phase, the angle omega t that's here, at some time omega t, or at some time t, I max is going to be right here. Well, guess what? The voltage is also going to be along that line. It's going to be bigger because the voltage has a bigger value to it, right? But it's still going to be along that direction. And so at some time t, the actual current is going to be this much. This is going to be the actual current, and we'll represent that by this arrow right here. This is the actual size of the current, and at that same time, the voltage, and let's draw it next to it, side to side, would be that big. Okay, so as you move with time, the current will go up, and then when both of these are right here, that would be at 90 degrees. You have the maximum current, you have the maximum voltage. And then as you go down, then again, we project this way, and the current would be less and less and less. And we can also do it on the bottom here because this is a thing that's rotating. So if we were down here, then the current being projected would be that big, and the voltage would be that big. It would be negative because now it's alternating current. Hey, hon. Helen, you got to come in on time. You're going to miss these things. Now, that right there is what we need. That is what we need to understand the next set of things, okay? So that was my diagram. Do I want to talk about something else before I go on? Yeah, let's talk about this other thing. So that's the phasor diagram. Okay, good. That's the phasor diagram that we want to know. And we'll get back to this in just a second. The other thing I want to know, look at this. The voltage is changing over time, back and forth, back and forth, back and forth. What if I asked you, well, if this is the voltage, it goes from high to low, what is the average voltage? If we were to look at this picture right here, you would get a high voltage, a low voltage, a high voltage, a low voltage, and it would go on forever. So if I asked you what the average voltage was, you would say 0, because you would have to take this plus that. When you add them together, that's going to give you 0. So that's not really going to help us if we ask for what the average voltage is. So instead, we have another type of average voltage that we'll look at. Let's take this voltage, right? And what I'm going to do is I'm going to square it. So I'm going to get voltage squared as a function of t will equal V max squared sine of omega t squared. So if that is my function, right, if I square this term and I plot it as V squared as a function of time, well, the graph of sine squared will never go to 0. Everything that's like going on the bottom axis goes up, and you like increase its size. So the graph of a sine squared graph would look something like this. Whoa, whoa, and so on. Okay? Where this value right here, where that value right there is going to be the maximum voltage. Can I erase this other part? I can. We don't need that anymore. So the highest value right here is going to be the maximum voltage squared. But I don't want that. What I want is the average of this. And the average, because this is symmetric going up and down, the average would be right in the middle. So I want this value right here, which is right in the middle of my graph. Okay? And we can call that V average squared. So that's right between those two values. Now, if you compare this to this, we can say that the average voltage squared is going to equal 1/2. It's only 50% of the maximum voltage squared. So far, so good. I hope so. And then if we want the average voltage, not the average voltage squared, then you have to square root both sides. That makes sense, I hope. So let's square root both sides, and we get the square root of V average squared is equal to V max divided by the square root of 2. So if we wanted the average voltage squared, we would have to do the maximum velocity divided by the square root of 2. And this has a special name to it. It is called not the average velocity, but it is called V velocity, voltage. V RMS, the root mean squared. So the square root of the mean value, the average, squared. And if you took AP Chem, I think maybe they do in Regents Chem too, you've seen VRMS for velocity when we're talking about thermodynamics, but this is voltage RMS. So it's the root mean squared, and the root mean velocity is equal to the maximum voltage. I keep saying velocity. The root mean voltage is equal to the maximum voltage divided by the square root of 2. And what's really cool is that the current also behaves the same way. If we repeated what I just showed you here for current, we could get the current RMS. So you can't even see that. Whoop, there we go. So I RMS is going to equal I max divided by the square root of 2. So this is going to be important later on, because when we're talking about voltages, we tend to talk about the root mean square voltage. We don't really tend to talk about the other term, the peak voltage. So the max voltage or the peak voltage is the highest value, but whatever. So we have that. Good. Let's do a quick example. Now, what is the voltage? What is the voltage in an outlet? Anybody know how much voltage you can get out of the outlet, the power outlets that we have in our homes? I'll give you a hint. It's a 3-digit number, and the first number is 1. Anybody know? 100, close. You're hot, but you gotta move up a little bit higher up. Keep going, keep going. Up, continue. Just a little bit more. That's right. No. Stop. 120 volts. So the outlet power is 120. Okay. I apologize. 120 volts. Now, that voltage, that 120 volts that comes out of your wall outlet, your wall socket, is actually the root mean square voltage, which means your power, the voltage that's coming out of the outlet isn't 120 volts. That's just the root mean squared average coming out. So if you wanted to know what the peak voltage is, well, we just use our equation here, we would say 120 volts is equal to the maximum voltage divided by the square root of 2. So the maximum voltage you would get, or the peak voltage, is equal to 170 volts. But you will not get 170 volts. 170 volts is just at the peaks. So when you were plotting this, whoa, it would only be 170 up here and here. So we don't really care about the 170. What we care about is this value right here. On average, it's going to be 120 volts because it's oscillating. All right. Do I want to mention anything else before we go on? Yeah, why not? Let's talk about power as well. So the power lost through the resistor, power dissipated. Well, power equation is usually written as I times V. But we're not going to be concerned about power. We're going to be concerned about the average power. And the average power is going to be equal to I RMS times the voltage RMS. And that's going to be equal to the power max divided by 2, not the square root of 2, remember that. And we'll work out, you can work out why that's going to be the square root of 2, not the square root of 2, but 2. So the other two equations for power in terms of resistors is I RMS squared times R. The resistor value doesn't change. It doesn't matter if you're alternating. A resistor is a resistor. It doesn't matter what the voltage is. We have that. And this is why we end up with 2 instead of square root of 2. But you can do that on your own. The other equation for the average power delivered through the system would be V squared RMS divided by R. So those are my average power equations. We're not talking about power. All right. So we'll do some problems maybe on Friday using all of these equations that we do. Now, this right here, there's a little caveat to it. There's something else I'm not putting there yet, but if we're talking about just resistors, this is fine. If we start adding capacitors and inductors, then we have to add a little factor to it called the power factor, and we'll discuss that another time. Speaking of capacitors, let's talk about capacitors. Okay, so just like I did with resistors, we're going to draw a capacitor resistor circuit here. So this is going to be the direct current situation first. And there might be a little tiny resistor there. We don't really care so much about that, but there needs to be a resistor here. Otherwise, you would short out your circuit. So this is going to be the capacitor circuit. And if we were to plot for a direct current, well, in the beginning, a capacitor behaves just like a wire. So you're going to get the maximum current. So if we were to do current as a function of time, it would start off here and go down like that. And that's going to be current as a function of time for a capacitor. And if we were talking about the voltage here, well, the voltage here is 0. And then over time, the voltage here becomes the voltage here. So the voltage as a function of time would do something like this. And it would asymptote to the voltage of the battery source. And that's the voltage as a function of time. So we knew that. We knew that, I hope. That's fine. You can see that the current and voltage are not in sync. The voltage and the resistor were in sync in this situation, the current and the voltage are not in sync. As one goes up, the other goes down, and that's the key. That's the key. So let us draw our AC circuit with a capacitor. So we got our AC power supply, and we've got our capacitor. All right. Need some water. So this AC power supply is has an angular frequency. Remember, it's got a frequency of 60 hertz. And so it's got an angular frequency of 2 pi times 60. Okay, so this thing is oscillating back and forth. Let's just think about, let's not even worry about the math here or anything like that. Let's just think about what's happening here. So the first thing that's going to happen is current is going to go like this, in here, and then come out of here, and then go this way. And as current goes in here and out this way, the resistance in this capacitor is going to get larger, because as you put charge here, remember the capacitor behaves like an infinite resistor. But the problem is this: as soon as you put current in here, you automatically take current out of it. That's what the whole idea of alternating current is. So if you were to do this really fast, if you were to put current in and take it out really fast, then the capacitor will never have a chance to behave like a resistor. It will behave more like a wire. So depending on the frequency, if the frequency of putting current in and taking it out, taking it in, taking it out is really, really fast, then this thing, this capacitor, isn't going to have much resistance to it. You get that? I hope so, maybe. But if you slowly put current through here, then it's going to charge it up. As it charges it up, the resistance gets bigger and bigger and bigger. And then you slowly take it out. Again, as you're taking it out, it's going to start off easy, but then it's going to become very, very resistive again. So the smaller the angular frequency is, the less current you will get. Okay? And so let's just write this down here, what resistance is going to be like. The resistance of this capacitor is going to be somehow proportional to 1 over the angular frequency. So the larger the angular frequency is, the less resistive this capacitor will be. The slower the current goes in and out, so the smaller this is, the larger that resistance will be. Remember that, because we're going to come back to this idea when we actually derive the equation. I hope you got that. I hope that made sense to you, how capacitors do this. So if I were to write down, at low angular frequency, capacitors behave like resistors. At high angular frequency, capacitors will behave like wires. That's the idea, and that's what this is saying right there. Let's take a look at it, though. So the current that's going in and out of the capacitor, the current that's going inside of the capacitor in and out, we can write like this. I is going to equal I max sine of omega t. Well, that's just what we had before. There's no problem there. The current is alternating because of this. It's going back and forth. What about, not this, what about the voltage of the capacitor? How is the voltage of the capacitor going to behave? Let me repeat that one more time just so we got that. I'm not asking you for the voltage of the power supply. I'm asking you for the voltage of the capacitor. How is that going to change as a function of time? So to do that, we're going to do it up here. The voltage of a capacitor as a function of time, well, that's going to be Q as a function of T divided by C. That's the equation for capacitance. And so we know that Q, we could write Q as another form, and that's going to be 1 over C, the integral of I as a function of T dt. Now, if you don't remember how I got that, let's just do it one more time, because you know what? Physics is fun. So we have Q as a function of T is equal to C times delta V, and you divide both sides by delta T, and then over here you get I, over here you get C dV over dt, and then you can solve for what could you do? You could bring the dt to the other side, and you get I dt is equal to c dv. And then from here, you can integrate both sides. So the integral here, c is a constant. We can bring it to the other side, and we end up with I as a function of t, or over here, sorry. What am I doing? The integral of dv is equal to 1 over c I dt. And this term right here is the voltage of the capacitor. There we go. So that's what I'm doing, okay? Sometimes we skip steps and then people forget where it's coming from. So this is where that idea is coming from. But hold on, we have I as a function of t written right here. So what I'm going to do is I'm going to factor out the I max. We got I max comes out of the integral over c. And then on the left, what's left on the integral is going to be sine omega t dt. So we solve this integral right here, and we will get, what are we going to get? The integral that is negative. So negative I max over c times omega cosine of omega t. And that's equal to the voltage of the capacitor as a function of time. Okay, so evaluate that integral. That's what you'll get. And then the last thing is this. I have a negative sign and I have a cosine omega. So negative cosine of omega t is actually equal to sine of, what is it, omega t minus pi over 2. Omega t minus pi divided by 2. And if you don't know why that is, let's just write it down here. The rule is that negative cosine of theta is equal to sine of theta minus pi divided by 2. That's the general, that's an identity, I suppose. Okay? So, if we replace negative cosine omega t with this term, we get the voltage of the capacitor is equal to, what are we going to say here? I max divided by c times omega sine of omega t minus pi divided by 2. Take a second and look at this and look at this. Look at this and look at this. Don't worry about these two right here. This is sine and this is sine omega t minus t. This is saying that the voltage of the capacitor is 90 degrees out of phase with the voltage of the current. It is 90 degrees out of phase with the voltage of the current. Well, what does that mean? What does that even look like? So we can plot our graph. Let's do I as a function of t first. So it's the sine graph that we're so used to seeing. And it's going to look something like that. Good. Okay. So this is I as a function of t. And then we're going to plug this term right here in, the voltage as a function of the current. And what would we get there? We would get, it is 90 degrees moving from here. So we have to shift 90 degrees, and then we can do the same sine graph. So it'll look something like, whoa, and then coming down, whoa, and then coming down like that. And that's going to be the voltage as a function of time. And it's the voltage of the capacitor as a function of time. Okay. Let's really pay attention now with our phasor diagrams here. Let's look at the current. The current is going to go up and then down. The voltage does the same exact thing as the current after the current does it. So the voltage will go up and then down. It follows the same pattern as the current, but later. So what we say is that what are we saying here? We say that the voltage lags the current by 90 degrees. So whatever the current is, the voltage lags it by 90 degrees. What does that look like on our phase diagrams, our phasor diagrams? It'll look something like this. Let's say this is the y-axis, the one that's important. Let's say the voltage of the capacitor is right here. This is the voltage of the capacitor, maximum. The current, and this is omega t, the current is 90 degrees ahead of the voltage. The voltage lags 90 degrees. So what I do is where this angle is right here, I'm going to make a right triangle, a right angle, like that. And this would be I max. And you can see that this angle right here is 90 degrees, or we call it the phase shift, phi. Okay? So I max is going to be omega t plus phi, or whatever. In the other case, this would be minus phi. And this would be our phasor diagram. And so if we wanted to know the voltage at this time right here, let's see here. The voltage, the actual voltage would be this much. This is the actual voltage from 0 to this value. And the actual current at that time would be right here. So the size of the voltage is this much, and the size of the current would be that much. And let's just do one more example. Let's put the voltage at 0 degrees. Let's just really hit home the point here of why these phasor diagrams are so beautiful. Let's say the voltage max was right here. So the current has to be 90 degrees from there. And that would be 90 degrees, right? So that's I max. Well, is that true? The projection of the voltage is 0. There's no height here. So when the voltage is 0, you get the maximum current. When the voltage is 0, you get the maximum current. Let's look over here. When the voltage is 0, that's right here in black, you get the maximum current. Over here, when the voltage is 0, you get the maximum current. And so this is our phasor diagram. And let me just tell you one thing. You can put a resistor on this phasor diagram as well. And you can also put an inductor voltage on this phasor diagram. And that's what we're going to need, and we'll do that tomorrow. When we put those three together, we're going to get this new idea. Okay? Now, the last thing I want to say about the capacitor is this. You're learning so much today. You're learning so much today. Is this term right here in the box. This term in the box is the amplitude of the voltage. Would you agree with that? This term right here is the amplitude. We could say that V maximum, that's the amplitude, is equal to I max divided by C times omega, the capacitance times omega. Now, if we're talking about voltage max and we had a resistor, we did have a resistor, the maximum voltage, it can also be written as I max times the resistance R. Oh, look at this. Look at this. You've got this equation and you got this equation. Look what happens. Look what happens. Please, please, with your eyes, look what happens. It's so beautiful. I maxes go away, right? So I maxes go away, and you're left with this. 1 over C times W, so the capacitance times the angular frequency is equal to R. No, it is not called R, because R doesn't change as a function of time. So we don't call this R. What we call it is, because it's the resistance of the capacitor, we have a special name for it. It is called XC. And that is called the capacitance reactance. So this is called the capacitance I can't even spell it. Capacitance, not resistance, but reactance. So the capacitance reactance also has the units of an ohm. But the thing with capacitance reactance is it's going to change with the frequency, the driving frequency of your AC supply. So if the frequency was 60 hertz, then you would get some capacitance resistance, reactance. If the driving frequency was 120 hertz, then this value would change. Why is that important? Because if we change the frequency, if we change the angular frequency, let's say W was equal to 60 rads per second to now W equaling 120 rads per second, this value would change. The resistance does not change. The resistance is a constant value. R, this resistor, will not change depending on what W is. However, the resistance of the capacitor will change with W, and that is why we cannot call it resistance. Resistance is meant for something that's not going to change over time. The reactance, how it reacts to the change in this, is where we get this term, the capacitance reactance. Okay, so the capacitance reactance is like this. And one more thing we can say about it is that omega, because it's equal to 2 pi times the frequency, that's what W is, we can say the capacitance reactance is sometimes written as 1 over 2 pi times the frequency C. So that's another equation for the capacitance reactance. Okay. Do you mind if I do the inductance as well? Give me a yes, and I'll continue on. If you're done, we'll stop it there. Just let me know. Are we good to do the last one? Yes, no, maybe? Okay, perfect. We'll need a little bit more time, just a little bit more time, and we'll finish. Connie didn't respond, so Connie's like, "Nah, I want to get out of here." All right, let's see here. Inductors. So the AC of inductors. So that cat in the box. So as we did before, let's just look at the direct current version first and see what happens there. So if we're looking at an inductor and we're doing the direct current as a function of time, right? In the beginning, you get a maximum voltage because the flux in the inductor doesn't want to change. So you'll get a maximum voltage, but over time, that voltage will decay down to 0. So that's V of the inductor as a function of time. Whereas the current, it's going to have no current in the beginning, but over time it's going to have the maximum current because this is going to behave like a wire. So we start off like this, and we'll go something like that. And that's going to be the current as a function of time. And you knew that. It's the opposite of what a capacitor does. Okay? So that's wonderful. That's wonderful. Everybody's happy. It's all great. Let's put the the alternating voltage now. And we've got our inductor here. And of course, we need a little tiny resistor. Otherwise, this isn't going to work at all. It's going to short out before you even do anything. So here's my circuit here. And with an inductor, the opposite is going to happen. So with low frequency, angular frequency, with low angular frequency, the inductor is going to behave like a wire. So behave like a wire. Whereas with high angular frequency, it will behave like a large resistor. And we knew this. So if you slowly allow current to go through here, eventually all the current's going to go through here, and it's going to behave like a wire. And then you slowly push it out, then it's going to behave like a wire again over time. But if you change the current too fast, then you're going to produce a large EMF. You're going to create a voltage that's going to try to oppose it. So if you have a high frequency, if you have a high W, it's going to be really hard to put in, and it's going to be really hard to take out if you do it really, really fast. But if you do it slow enough, it'll start to behave like a wire, which is the opposite of what a capacitor did. At low frequency, the capacitor behaved like a resistor, and at high frequency, the capacitor behaved like a wire. So an inductor does the exact opposite when you change the size of the frequency. Okay, so let's start off with the current equation that we had just like we did before. The current that's being generated from the system is I as a function of t is equal to I max times sine of the driving frequency times t. And we're supposed to write a little d here as well because it's the frequency is coming from here. But for now, who cares? We don't need that. But we should. So what I want to know is what is the voltage of the inductor as a function of time? Last time we did the voltage of the capacitor. How do we find the voltage of the inductor? Let's do it. Let's do it over here. All this space that I got. The voltage induced, the voltage of an inductor is given by the change in the flux divided by the change in time. That's the equation for the voltage of the inductor. And the flux is really just L times I, right? So that's what the definition of the flux is. And we can factor out the L, and we get that the voltage of the inductor really as a function of time is going to equal L times di over dt. But wait a minute, we know what I is. I is given by this equation right here. So we can write that as equal to L times d dt of I max sine of omega t. And what do we end up with? We can pull out the I max, and this is just chain rule. We end up with the voltage of the inductor as a function of time is going to equal L times I max times omega cosine of omega t. Okay, so that's what that is. Now, wait a minute. let's get the inductive capacitance first, and we'll worry about the phasor next. This term right here, all of this right here, is the voltage maximum. So that's L times omega times I max. But wait a minute, the voltage maximum can be written as I max times R. Remember that? And look at this. That cancels out, the I maxes cancel out, and we've got our new equation. It's no longer R, this isn't R anymore. We call it the inductive reactance, XL. And the inductive reactance is simply just L times omega. And it's consistent with what we had said. If the angular frequency goes up, the resistance will go up. If the angular frequency goes down, then the resistance of the inductor will go down. And it's the same thing with capacitors. If we just put the capacitors here, the inductive capacitance, it was 1 over C times omega. And so this is inversely proportional. So as omega goes up, the resistance will go down. Remember in the very beginning of this, I said, hey, you remember this if you want to know anything. Resistance is somehow going to be proportional to 1 over that. Well, that's what that came from. The resistance for an inductor is going to be proportional to the, not that, 2W for an inductor. And that's what we got there. So this is called the inductive reactance, and this is called the capacitive reactance. The units for this are ohms. The units for this are ohms. So they're like resistors, but like varying resistors over time, if you want to think of it as anything. And here's the really, really cool thing about this. When we're talking about AC circuits, we don't really talk about R anymore. I mean, there's R's in there, but we don't call it resistance. When we combine resistors, capacitors, and inductors together, the resistance between all of them is no longer R. The word that we use is Z. And you probably know what the Z stands for. It stands for Zoe. So Zoe is, no. Z is actually the letter, and the Z stands for impedance. And if you think about it, that makes sense. In the English language, impedance is sort of like resistance. It's impeding you from moving forward. So when you combine the resistance plus the... Of course I did. Just like you remembered to put... You put the little Spanish sign for torque. So everybody remembers everything. So Z is equal to the impedance, and it's the combination of resistors, reactance of capacitors and resistors, and all of that is that new form of impedance. You could sort of think of it as like the equivalent resistance. That's what it is. All right. So let us graph this. So the voltage as a function of time, let's quickly write that down. Oh, drop my eraser. The voltage is going to be, oh, what did I say? The voltage of the inductor as a function of time is going to equal V max times cosine of omega t. Now, wait a minute. I don't want it in omega. I want it in sine because I like sine. You know why? Sine's cool, man. So sine, why do I keep writing sine? Cosine of omega t, well, you could have an identity for that, is really just sine of omega t plus phi, or plus pi over 2 here, instead of minus pi over 2. And so the voltage of an inductor is going to be written as V max sine of omega t plus pi divided by 2. And we can see that the voltage is actually going to be now, the current is going to be lagging the voltage. Well, let's plot it. So the current as a function of time is just your typical sine graph. So it'll look like this, and then come down like that, and so on. Now, if we were doing the sine omega t plus, this is just cosine, but we would have to shift it back a little bit. And what we would see is something like this. There we go, beautiful. So that's the voltage of the inductor as a function of time. And the thing in the red is the current as a function of time. And you can see that, whoop, let me get my eraser. You can see that what the voltage does first, the current does afterwards. So in this case, the current is lagging the voltage. And so when we draw our phasor diagram for an inductor, if we draw our phasor diagram, let's start with Vmax first. So this is the maximum voltage of the inductor, V max. The current would be 90 degrees from that, and this is pi over 2. I mean omega t. The current would be, where we write it, 90 degrees out of phase with that, but it wouldn't be leading, it would be lagging. So it would be like that, and that's I max. And so at this specific frequency, you would have a voltage that's this big. That's the actual voltage during this time period. And the current would be that big. And what's interesting is that the voltage and the current are in opposite directions. And that's what you should expect when we're dealing with inductors. Inductors kind of prevent you from changing the flux or whatever. So that's the voltage, that's the current at this specific time. And that is a phasor diagram for inductance. If we were to put everything together, and we can, it's an RLC circuit, we could put this here. We could then put, this could be the voltage of the resistor. We could put the voltage of the inductor, and we can put the voltage of the capacitor all together. And then somehow we can come up with the impedance equation. But that will be for tomorrow. For today, my goal was to at least show you all of this. I hope you got everything. What I wanted you to know, let's just quickly review, is the RMS. I wanted you to know RMS, the IRMS, so the root mean square of those two. I wanted you to know that the voltage of the resistor is in phase with the current. The voltage of the current is out of phase by 90 degrees for both the inductor and the capacitor. And the last thing I wanted you to know was how to utilize these phase diagrams for individual voltage, current, voltage, resistors, inductors, capacitors. So if you got all that, good on you. You've just learned a really big solid chunk of AC circuits. And I'm telling you now, I wish I had known this before I took this stupid class. But anyways, this is really useful if you're going to be an engineer. Electrical engineer, that is. That's the only real type of engineer.